All right, guys, now we move to the next topic, which is the titration of weak acids and bases with the respective strong base or acid. As I mentioned at the beginning for this chapter, we're actually not going to be doing the calculations for these titrations of weak acids and bases because of the fact that they are quite involved, and unfortunately we don't have enough time because of the loss of a week. So what we will be talking about is the conceptual aspects of that titration, which are very important for you guys to know. So let's go ahead and get started. All right, so to begin with, here is the view of a weak acid strong base titration. What that means is that we're starting with a beaker that is full of a weak acid. Whoops. We have a beaker, sorry, that is full of a weak acid, let's say HNO2. And to that beaker, we're going to be adding through a burette our titrant, which is going to be a strong base, sodium hydroxide in this case. We're going to be monitoring the pH inside of the beaker, and so of course at the very beginning, before we add any sodium hydroxide, all that we have is the nitrous acid, and because of that we're going to start with a low pH, and then as we start adding more and more of the sodium hydroxide titrant, then the pH is expected to rise. Now, if you compare the look of this particular titration curve to that of a strong acid, strong base titration, what you might see immediately is, first of all, that the initial pH is going to be higher than that of a strong acid, right? Because the strong acid is going to have a higher concentration of hydrogen ions, and because of that, the starting pH is going to be lower if we are comparing two acids of the same concentration. The next thing that I want you to see is that the rise of the pH near the equivalence point is going to be smaller. You can see that it's less sharp than that which we saw for a strong acid, strong base titration. And the other thing that I want you to see is that at the equivalence point, the pH is not going to be 7. Regardless of what weak acid you are titrating, the pH is not going to be 7. Or even if you were titrating a weak base with a strong acid, the pH also would not be equal to 7. In this particular case, we're talking about weak acid with a strong base. And for that particular case, your pH at the equivalence point will always be greater than 7. And that's what I have here. This is for the case of a weak acid titrated with a strong base. This will always be the case because of the fact that when you do this titration, this reaction, the salt that you're forming is a basic salt, and so the solution that you end up with at the equivalence point is going to contain the salt and is going to contain water, and of course the salt is going to be responsible for setting the basic pH of that solution. All right, the other thing that I want you to see is that the pH at the halfway of the equivalence point, which is going to be equal to the pKa. So let me go over that again. So the pH at the halfway of the equivalence point. We know that the equivalence point is going to be whenever we reach this right here, right? Halfway in between the titration curve, that's where we reach the equivalence point. Remember that the equivalence point is the point where we have an equivalent molar ratio of the acid to the base according to the balanced chemical equation. In this particular case, a 1-to-1 molar ratio. The halfway to the equivalence point, which is also known as the halfway point, is basically going to be whenever we have added half of the amount of base that we need to reach the equivalence point. So let's say, just for kicks, like let's make up a number. Let's say that to reach the equivalence point, we needed 50 milliliters. Then the halfway point would have been whenever I would have added a total of 25 milliliters of my titrant, meaning that I have added half the number of moles of my titrant that I would need to reach the equivalence point. And at that point, what is interesting is the fact that the pH is equal to the pKa. So this is one calculation that I could ask you. If I have you, if I give you enough information for you to figure out the number of moles of your weak acid and the number of moles of the strong base that you are titrating, and if the number of moles of the base happens to be half of that which the acid is in, then you could say that you are at the halfway point, and because of that, the pH is equal to the pKa. So again, pay attention. If you have half the number of moles or half the volume that you need to reach those moles, then your pH is going to be equal to the pKa. For this kind of problem where you're figuring out if you are at the halfway point, it is very important that you actually look at the number of moles because that is what determines whether you are or are not at the halfway point. The volume can help, assuming that you know what volume you would need to reach the right number of moles. But you should always kind of pay attention to the number of moles. That's what would tell you if you are at the halfway point or not. All right, let's move on to the next one. This slide is also important. It has a lot of conceptual information. So let's start with this. We are titrating weak acids with strong bases. So as expected, we're starting with low pH, and the pH increases as we are more of the titrant, which is a strong base. In this particular graph, what I have is actually a strong acid at the very bottom that is titrated with a strong base. And then all of the other curves correspond to weak acids that have different Ka. Just to remind you, the weaker the acid, the smaller the Ka. So for example, this acid that has a Ka of 10 to the minus 8 is actually the weakest out of all of this. The one that has the Ka 10 to the minus 2 is going to be stronger than all of this, but is going to be weaker than the strong acid itself. All right. The weaker the acid, the higher the initial pH, and I'm hoping that you guys can see that here. Notice that the weakest of the acid, and I'm going to go ahead and label it weakest here, the weakest acid actually starts the titration at the highest pH, right here at about 4.5, while the stronger out of these weak acids is going to start with the lowest pH, which in this case is 1 point something. The next thing, the weaker the acid, the smaller the rise near the equivalence point. Again, remember that we typically have a rise in the pH as we reach that equivalence point, but that rise, how much we actually increase, is going to be smaller for the weakest of the acids, compared to the red one, which is still a weak acid, but it still has a significant rise as we get near that equivalence point. Finally, the weaker the acid, the higher the pH at the equivalence point. The little open circles here represent the pH at the equivalence point. For the strong acid, we know that if a strong acid is titrated with a strong base, then the pH at the equivalence point is equal to 7, which is this one right here, the first of the circles. pH is equal to 7 for strong acid only. But for all of the weak acids, the pH at the equivalence point is greater than 7, as we already said, because of the fact that the salt that is formed is no longer a neutral salt, but instead it is a basic salt. So the other thing that I want you to see here is that the stronger that weak acid is, or the weaker, I should say, the weaker that weak acid is, the higher the pH at the equivalence point. For example, for the red one that has a fairly large Ka, we are starting with a pH of about 7.5 maybe at the equivalence point, and that increases all the way to 10.5 maybe for the weakest of these weak acids. So it can be quite basic at that point. All right, we're going to go through a number of questions that I hope that you guys will actually pause the video and give them a try. So let's start with the first one. Assuming that an equal amount of the following weak acids is titrated with 0.1 molar NaOH, determine which acid would have the highest pH at the equivalence point. So we are titrating weak acids with 0.1 molar sodium hydroxide, meaning a strong base. So I'm just going to write here, we have weak acid, strong base titration, which are the ones that we just discussed. And what we're looking for is which one is going to have the highest pH at the equivalence point. All right, so highest pH at the equivalence point, according to the previous slide, would have been the weakest of the acids. And the weakest of the acids would be the one that has the smallest Ka. And since the information that we actually have is pKa, not Ka, so we need to look at the relationship between pKa and Ka. You guys know that pKa is equal to the negative log of the Ka. And the larger, or actually since we're talking about the smaller the Ka is, the larger the pKa is. So in this particular case, we were looking for the smallest Ka, and therefore we are looking for the largest pKa. So the answer for this particular problem is actually the pyridinium ion, which has a pKa of 5.23. All right, the next question. Oh, rats. All right, so now we're going to be looking at a whole titration curve for a weak acid, strong base titration. Let me go ahead and label that here, weak acid plus strong base titration. For this particular case, we have acetic acid that is being titrated with sodium hydroxide. Of course, the product of that titration is going to be a salt, sodium acetate specifically, and water. Just like with the strong acid, strong base titration, we're going to have four main regions. The first region, A, is actually the starting point where we have added 0 milliliters of the titrant, 0 milliliters of sodium hydroxide. And so because of that, all that we have is the weak acid. Since it is a weak acid, we can't just calculate the pH by taking the negative log of the concentration of the acid, because remember that the acid only partially dissociates, and so the concentration of hydrogen ions is going to be much lower than the concentration of the acid itself. And so realistically, what you would do in this kind of case would be to find the hydrogen ion concentration by utilizing an ice chart. And once you have that hydrogen ion concentration with an ice chart, you will then use that to find the pH by taking the negative log of that hydrogen ion concentration at equilibrium. I'm going to put AQ for equilibrium. All right. In stage B, that stage is known as the buffer region. And it is known as the buffer region because of the composition of the solution in that region. So if you think about it, in this region, before the equivalence point, it means that I have acetic acid in my container, and I have added some sodium hydroxide, but not enough to completely consume the acetic acid. So you're going to have some leftover CH3COOH, some leftover weak acid. Now, all of the sodium hydroxide that got added did react with some of the acetic acid, and in doing so, it has formed some of the salt. So even though the sodium hydroxide has been consumed, I do have some salt in that solution. And of course, I have formed some water, but the water is not going to have an effect on the pH. So if you notice, the two things that we have present now in our solution are a weak acid and its conjugate base in the form of a salt. And that right there is exactly the two things that you need in order to make a buffer. So this is the reason why this is known as the buffer region. Again, because basically what you have is the weak acid that is left over or that is present in excess, and you have now the conjugate base of that acid in the form of a salt as a product. And so the interaction between these two is going to lead to a buffer behavior. To calculate the pH in this range, what we would typically do would be to find what is the number of moles of the acid that is in excess, what is the number of moles of the salt that is found or that is formed, and we do those calculations by using an ICR chart. And then once we are done with this process, we would then go and utilize the Henderson-Hasselbalch equation in order to find the pH of the new solution. So just so that you have a little bit of notes, I'm going to put that information here. you would use an ICR chart to find the number of moles of the weak acid, I'm going to call it HA, in excess, and to find the number of moles of the salt that has been formed. And once you have that information, you would utilize it in the Henderson-Hasselbalch equation to find the pH, and that is for the buffer region. All right, so now we go to region C, which is the equivalence point. What I really need you to remember is that at the equivalence point for a weak acid strong base titration, the pH will not be equal to 7. In fact, the pH will be greater than 7. And that's something that you absolutely must know. pH is greater than 7 at the equivalence point. The reason, as I mentioned before, is that at the equivalence point, you have completely reacted all of your weak acid with the equivalent amount of base. And so you have neither of the two in excess. In fact, the only things that you have in your solution are going to be the salt and water. And that salt happens to be a basic salt. So if you were going to do the calculations for this particular case, what you would do would be to find the pH of the salt solution. And we learned that at the end of chapter 16. But in this particular case, it's a little bit complicated because you need to calculate the molarity of the salt in that new solution, which requires that you figure out the number of moles of salt formed, you figure out the new volume, you find the new molarity, and then from there you go on. And so it involves a nice chart, and it's complicated. It's a very lengthy calculation, which we're not going to have time to go over. And then finally, region D is going to be what happens after the equivalence point. So after the equivalence point, you no longer have any acid because all of the acid has been consumed, but you kept adding sodium hydroxide. And so now what you have is an excess of sodium hydroxide, which will be controlling the pH. So for part D, we basically would find the number of moles of the base, NaOH, in excess. And from that information, we could then find the molarity of hydroxide ions, and from that, the pOH and the pH. So this region D, is actually the exact same calculations that we did for region D for the strong acid, strong base titration. Exact same calculations. All right. As I mentioned, we are not actually going to go over the calculations for each of these stages. You will not be asked about those on the exam because of the lack of time. However, any of you who are chemistry majors or chemistry minors, you guys might want to get some additional information either from me or yourselves or through other professors because these concepts are going to become important once you get to quantitative chemistry or quantitative analysis. All right, let's go ahead and move on. We will be skipping this, but I give you the slide that shows you what is the procedure that we follow in order to do the calculations. Again, if you're a chemistry major, I encourage you to look at this and to ask questions. And same thing for the next slide, which we will be skipping because it requires calculations for every single stage of the titration. If you do want to do it, have at it, and I'd be happy to provide the solutions, of course. All right, so now some questions that you should be able to answer. Give it a try. The pH at the equivalence point of a titration between a strong acid and a strong base will be, and so the key thing here is that we're titrating a strong acid with a strong base. And we know that at the equivalence point for such a titration, the pH will be equal to 7, only for strong acid, strong base titration. All right, next question. The pH at the equivalence point of a titration between a weak acid and a strong base is going to be, well, we just talked about that, and the answer is that it is going to be greater than 7 whenever you have a weak acid titrated with a strong base because of the fact that we are forming a basic salt. Next question. All right, the pH at the equivalence point for a titration between a weak base and a strong acid will be. Well, we actually have not talked about this just yet, and we will in just a few slides, or in the next slide for that matter. But basically, the behavior is going to be the complete opposite of a weak acid strong base titration. Now we have a weak base and a strong acid, and so we should expect that the pH at the equivalence point will actually be less than 7 because of the fact that you will be forming an acidic salt. All right, which of the following titration mixtures will produce an equivalence point pH which is less than 7? Give it a try. Right, so a pH less than 7 at the equivalence point means that we are titrating a weak base with a strong acid. And so our job is to figure out of this which one is the combination of a weak base with a strong acid. This particular case, it's not looking good because this is a strong base, so that's not going to work out. In this particular case, I have a weak acid with a strong base, so that actually will not work either. The next one, I have ammonia, which is a weak base, so that's looking good. And then I have hydrochloric acid, which is a strong acid. So that definitely complies with what I'm looking for. And then the last one, this is a strong acid with a strong base, and therefore that will not work out. Whenever you have a strong acid and a strong base, as you do in A, B, and D, what you have at the equivalence point is a pH that is equal to 7, so not less than 7. Next question, which of the following will produce a titration mixture with a pH less than 7 at the equivalence point? Give it a try. All right, so same idea. pH of less than 7 at the equivalence point means that we're working with a, a weak base that is being titrated with a strong acid. And so again, our job is to figure out which of these is actually matches that. First one, we have a weak acid with a strong base, so that's not it. Second one, this right here is pyridine, which we had talked about before, and we said that that was a weak base. So that's looking good. And then that's reacting with nitric acid, which is a strong acid. So that right there is a perfect choice. The next ones, we have strong acid, strong base. So that one does not qualify. The last one what we have is a weak acid with a strong base. So if that were the case, the equivalence point would actually have a basic pH, meaning that the pH would be greater than 7. So that is not the right choice. All right, this slide, I should have put it earlier, but basically this slide shows you what happens with a weak base, strong acid titration. For example, we could have ammonia reacting with hydrochloric acid. The end product of that reaction is going to be a salt that is basically taking the, this should be NH4Cl, I apologize. It should take the this guy after it has accepted a proton, forming NH4, and then combining with the chloride ion that is formed. So your salt comes from the combination of those two. Now, as you see, what happens in that titration is that we're starting with a high pH because we're starting only with the weak base. And then the pH is going to decrease as we add more of the titrant, which is a strong acid. Notice again that the pH change near the equivalence point is not nearly as sharp as it would be with a strong acid, strong base, or in this case, strong base, strong acid titration, right? It's a little bit more gradual. In addition to that, and most importantly, notice that the pH at the equivalence point is not equal to 7. In fact, it is actually less than 7, which is something that is very, very important for you guys to remember. And hopefully with the problems that we just did in the previous few slides, that actually got ingrained in your brains, hopefully. All right. And the other thing that I wanted to mention is that the pH at the halfway point is also going to be equal to the pKa. Of course, in this particular case, the acid, which is hydrochloric acid, which is a strong acid, doesn't have a pKa. It doesn't have a Ka because there's no equilibrium for that. So in this particular case, what we're talking about is the pKa of the conjugate acid of the weak base. What that means is that, okay, let's say that I am at the halfway point. Halfway point would be wherever I have half of the moles. So let's say that here, let's say that it was required 50 milliliters to reach the equivalence point, and let's say that those 50 milliliters were equal to, I don't know, 0.1 moles. Then at the halfway point, which would be wherever I have added 25 milliliters, which means that I have added half of the number of moles, so 0.05 moles. Then at that point, I know that the pH is going to be equal to the pKa. But the pKa of what? What I need you guys to think about is the fact that we're dealing with a weak base. And so for that weak base, you can go and you can find the Kb of the weak base on a chart. And then you can think about the fact that that weak base has a conjugate acid. In this particular case, the conjugate acid of ammonia is going to be the ammonium ion. And I can find the Ka for that conjugate acid by basically taking Kw and dividing it by the Kb of my base. So that's basically what we would do in this particular case. We would go and we would find a Kb for ammonia. We would then convert that into a Ka for the conjugate of ammonia by taking Kw over Kb to find the value of Ka. Once we had the Ka, we can take the negative log of that to basically be able to get our pKa, which is the pH at the equivalence point. That kind of calculation I can ask you, right? And that's only the calculation at the halfway point or halfway equivalence point. All right, we will be skipping this other calculation. But again, if you are inclined to do it, I'd be happy to provide the solution to it. And let's move on to the titration of polyprotic acids. So remember that a polyprotic acid is an acid that has more than one acidic hydrogen. And so because of that, it is able to donate not just one, but two or maybe three hydrogens depending on its structure. Examples of polyprotic acids were things like sulfuric acid or phosphoric acid. Here I'm representing a polyprotic acid by putting H2A, where A just represents an anion, any anion. Now, the titration curve for a polyprotic acid is going to look something like this. And the reason why it looks so different is that basically you're going to have more than one equivalence point. In fact, you're going to have one equivalence point for each ionizable acidic proton. So, for example, this acid has two ionizable or two acidic hydrogens. And so for each of those acids, I'm going to have one equivalence point. So in this particular case, we're going to have two ionizations, so two equivalence points. At the beginning here, the component that is most representative is the H2A. Once I reach to the equivalence point and pass the equivalence point, the substance that is present in most concentration, if you would, is going to be the first conjugate acid of that, which is HA-. After that, we're going to pass to the second equivalence point, and the substance that is going to be present is going to be A2-. We will not be doing any calculations on these kind of titrations. We just want you to be informed about them and just kind of be able to recognize, if I show you a plot like this, can you figure out that this is the titration curve for a polyprotic acid? And can you also determine with which kind of acid that would go? So if it has two equivalence points, it means that I started with two acidic hydrogens or two hydrogens that could be ionized. All right, the last part that we're going to be talking about is indicators that are utilized in acid-base titrations, which is section 17.5 of your book. All right, we already mentioned in the previous chapter that in order to measure pH, we have a variety of technologies or techniques that can be used. One of them is the use of a pH meter, which would enable you to get electronic readouts throughout the titration process. But if you don't have access to that, then you can use pH indicators, which are substances that have different color at different pH, as is shown here with the example of anthocyanin, which is obtained from red cabbage, and which gives you a range of colors for acidic pH all the way to basic pH. Right? We can do that in solution as is shown here, or we can also utilize a pH paper that is impregnated with such indicator to give us a color readout of the pH of our solution. All right, so how do we select these pH indicators, or how do those pH indicators actually work? As I mentioned, they are substances or molecules that have different colors at different pH. They actually consist of weak acids or weak bases that have a conjugate that has a different color. The color change for those substances is going to occur near the pKa of that indicator. And so the pKa of the indicator is an important piece of information because we want the pH to change, or actually we want the color to change at a pH that is of relevance to us. And so we need to make sure that the pKa is going to be in the range of the pH that we are interested in. Now, the color change of the indicator is known as the endpoint of the titration, and that is something that is important to know. And as I mentioned before, that endpoint is related to the equivalence point, but that they're not necessarily exactly the same. They are close to each other if you select the pH indicator correctly. Now, the reaction right here is showing the equilibrium of the indicator in its acidic form and then in its basic form on the right, once it actually has donated a proton. So in its acidic form, the indicator is actually red. And in the basic form, and in the basic form, the indicator in this particular case is actually yellow. What color do you think that it would be in between, in the pH where it's changing between its acidic form and its basic form? Well, of course, it would be the color in between red and yellow, which is orange. All right. So just to reiterate, the equivalence point of a titration is where you have exact neutralization, meaning that you have added the right molar ratio of the acid to the base or of the base to the acid so that they completely consume one another. The endpoint of the titration is the point at which the color changes because the indicator is going from transition from its acidic to its basic state. So an appropriate indicator for a titration must change color over a range that overlaps or is close to the equivalence point. So basically, this is what you need to remember. The fact that to select an indicator for a titration, you need to make sure that it changes color close to the equivalence point, close to the pH at which the equivalence point is located. And because of that, you need to look at the pKa of that indicator and select one that is close to the pH of your equivalence point. So the goal is that the indicator changes color within the most vertical portion of the titration curve, which is at the equivalence point, and that is typically within plus or minus 1 unit from the equivalence point. This is something that is good for us to remember. So we want the indicator to change color within plus or minus 1 pH unit of the equivalence point. And so to do that again, we're going to be looking for the pKa of that indicator and matching it with the pH at the equivalence point if we know that already. If you don't have a table that has the pKa's or the Ks of those indicators, you might instead have access to like a graphical representation of the color change of those indicators as a function of pH. So you can look at the color change in the pH range that you are interested in and be able to select the right indicator that changes near the pH where you expect the equivalence point to be. Just to let you know, your book, the online book in Sapling, has this figure 17.4, which has an interactive simulation of titrations and indicators. You can utilize it to see how to select an indicator, but most importantly, you can also utilize it to look at the plot and the concentrations of the acid and base and the pH as a function of titrant volume. So I encourage you guys to play with it a little bit and see if it helps you understand the concepts more conceptually. All right, note that the pH at the equivalence point and the shape of the curve in the titration curve. So this is something that I want you to pay attention as you are working in this interactive simulation. The pH at the equivalence point and the shape of the curve at each titration. Also in this interactive simulation, you're going to see these bar graphs that show you the relative quantities of the acid, the base, the salt, and the water that you are dealing with in each stage of the titration. So again, it's a good way for you to get very good conceptual understanding of what is happening in the titration. All right, so selection of indicator. Sorry, so we said that we want to select an indicator that ideally changes color very close to the equivalence point of our titration, right? And so, for example, in this titration, we're titrating a weak acid with a strong base, and we can see that just by looking at the shape of the curve, right? I know that it's a weak acid that is titrated with a strong base. It's the same titration on the left and on the right, right? We know that the equivalence point is at about 9 in this particular case, right? pH of 9 at the equivalence point. So we need to select an indicator, and we have two choices. One of the choices is phenolphthalein, which has a color change in the range of 8.3 to 10. It actually goes from clear, so it is clear from pH 0 all the way to pH 8. Then it starts transitioning to purple, and then after pH 10, it is always purple. So and then the other choice that we have is methyl rate indicator, which has a color change in the range of 4.2 to 6 down here. So I want you guys to think about this. Like if you're doing this titration, would it be better to utilize phenolphthalein, or would it be better to utilize methyl red, which goes from red at low pH to then being yellow at high pH? And notice the region or the pH at which the color change occurs. Think about it. And now I will tell you my choice. So the pH indicator that would work best in this particular scenario is phenolphthalein. And the reason for that is that you can see that the color change occurs right on top of the pH change at which we have of the pH at the equivalence point, which means that that indicator would actually tell me when the equivalence point has been reached. On the other hand, here, if we started utilizing the methyl red indicator, my titration would be red initially, or orange, I should say, initially, and it would actually change to yellow at a very early stage, and I would not know when I reach the equivalence point because I can keep adding, and the color would no longer change, right? So I would not know when I reach the equivalence point. So for this particular case, phenolphthalein would have been the right choice. Now in the next example, we are doing the titration of a weak base with a strong acid, and I know that because of the shape of the titration curve, and I also know that because the pH at the equivalence point is 5 in this case. So it's an acidic pH, meaning that I have a weak base titrated with a strong acid. We have the same two indicators, phenolphthalein on the left, methyl red on the right, and we have to select which of the two is going to be best for our particular titration. In this case, phenolphthalein is not going to be the choice because it would change color and become clear very early on in my titration, and it would not tell me when we have reached the equivalence point at all. On the other hand, methyl red actually would work really well because its color change overlaps with the pH at the equivalence point of our titration. So this one would have been the right choice for this particular titration.